All right, so the first thing we're going to start talking about is vectors. We're going to use vectors a lot in this course, and so we're just going to go through and review some features of vectors that are going to be really important to us. And so let's go ahead and get started. So vectors, we're going to find that there's two kinds of physical quantities that we will deal with. A scalar only has a size, so a quantity that can be described with only one number, and this quantity is called the magnitude. And so some examples are time, speed, which is just a magnitude, say 5 miles per hour. And then there's vectors, which has a size and a direction, which in general are going to be more difficult to deal with. And so you can describe it with two numbers, a magnitude and the direction, and we'll go through a lot of different ways to kind of describe vectors. And so we're going to be able to need to describe vectors, and to add and subtract vectors will be really important to us. And some examples there would be the position of something, the velocity. So the velocity is a vector, the magnitude, say 5 miles per hour, but it also includes the direction, say you're heading north, where the speed is just the magnitude. So that's something we'll talk about. And so let's start with a question here. So which of the following are not vectors? So go ahead and pause this and think about this, and then we'll come back and talk about it. All right, so I got C. So the following that are not vectors, so we got time is not a vector, speed, as we just talked about, is not a vector, and then temperature is also not a vector. So these three things have just a magnitude associated with them, and then velocity and position are going to be two of the most important vectors that we will deal with as we go through the course. Now, so there's two ways to represent a vector, and so let's go through and sort of figure out these two ways. So the first way is analytically, so the mathematical way. And so, for instance, one way we can write a vector, so oftentimes we write a vector, we'll write it in like a little parentheses form here. And so this is a velocity, the one we talked about earlier, where the magnitude is 5 meters per second, and the direction is north. So that's a totally fine way to represent a vector. And then there's a million ways to kind of talk about this. So 5 meters per second. So let's suppose we have a sort of an XY axis like this, and then this direction is assumed to be our north. Then you could say 5 meters per second, 90 degrees from the x-axis, something like that. So as long as you're specific and tell us what you mean, there's lots of ways to kind of represent that. The second way is geometrically, and that's the arrow method. And so the arrow points in the direction that the vector does, and the length of the arrow is its magnitude. Now it's possible for us to do a lot of the stuff we're going to do geometrically, but it generally takes more time. And so usually the geometrical way will be sort of something that we'll do is drawing a picture to kind of help us see the picture a little bit better. Now, I'll often bring up questions. Here's a question I got from a student. So the only thing I'm confused is in math class we used represent vectors with the x and y coordinates. So we'll do that a lot as well. But it's totally fine to talk about the vector in terms of its length and its direction. And so if there's a question on a homework or something, we'll usually specify what way we want these represented. So to help you figure that out. So here's a really key part of stuff that we're going to do. We're going to use this all the time, probably like every day. So it's right triangle trigonometry. Again, it's something you've seen before, but this is one of the more common things that I think people come in a little bit rusty with. And so in general, we'll be able to represent a lot of our vectors. We'll be able to draw a little right triangle like this. And so using your right triangle trigonometry can be really helpful. And so the big key part here is SOHCAHTOA. And so so is sine is opposite over hypotenuse, ca is c is adjacent over hypotenuse, and tangent is opposite over adjacent. And so basically what that means is there's these four pieces: the length of the hypotenuse, the length of the opposite, the length of the adjacent, and then the angle. And if you know two of them, you can find all the others. And so a lot of times we'll be given just a certain amount of information, and it'll be really helpful for us to find the different sides, to break it into these x and y components as that student was talking about. And so here's an example. So what is the length of the adjacent side? So we're given an angle, we're given the hypotenuse, and we want to know what's the length of the adjacent side. So go ahead and stop, pause this and give this a go, and then we'll talk about it. All right, hopefully you got choice A. And there's lots of ways to do this, but the way I thought about doing it is you say, okay, well, cosine 38 gives me, from our formula, adjacent over hypotenuse. And why did I pick that? Well, because we're trying to find the adjacent side. And I knew that we have the hypotenuse side of 6 and the angle. And so I knew that we would have everything else that we need. And so I can say that A equals the hypotenuse times cosine 38. And of course, the hypotenuse is 6 meters times cosine 38. Now you can plug in your calculator, or I also gave these numbers over here as well. And so when I plug this in, I got 4.73 meters. So this will be something that we'll do a lot. It'll be really helpful for us to be able to take vectors and find like their adjacent components and their opposite components. Another thing too is if this is something that you're a little bit rusty with, we have the pre-lecture videos that I have as well that goes a little bit more in depth into this. And so that'll be the case with most of our lectures. There'll be a pre-lecture video, and the idea there is it's sort of a little bit more information if the lectures weren't sort of enough for you. Now, another thing that we'll do is kind of doing the opposite. Here we have 2 pieces of information, and we want to use this to find the angle. And so here we have a situation where there's 7 meters and 6 meters, and we want to find that angle in there. So go ahead and see if you can do this one here. All right, so I got 49.4. Hopefully you got that too. So I chose to use TOA for this one here. And so that says the tangent of the theta equals opposite over adjacent. And so we can use, take the inverse sine, or I'm sorry, inverse tangent of the opposite over adjacent to get the angle. And of course I did this because we were given the opposite as the 7 and the adjacent as the 6. And so when I plug this in here, I get 7 meters over 6 meters, and when I plug that in, I got 49.4 degrees. So now we're going to do an example that's a little bit more like what we'll be doing in this class. And so here we have a vector C, which has an angle phi with respect to the y-axis. And I want to know is what's the x component of the vector C. And we'll assume here that we have our typical y and x axis, which kind of looks like this here. So we got like the positive y goes that way, and the positive x goes that way. Give this one a try, and we'll come back and talk. Okay, so for this one, I got choice C. So let's maybe go through and unpack this one a little bit. And so what we're trying to do here is I want to find, what you're doing is trying to find the y component as well as the x component. So I'll call these cy and cx. And technically, the hypotenuse is going to be the absolute value of c there. And so that's how we're going to sort of call that here. And so for the x component, now how would I do that? Well, so we're given this angle here. And so the x component is going to be the opposite from the angle. And that's unusual, right? It'll be really often that the x component will be the adjacent side, which will be the cosine, but it won't be always. And so you got to be real careful about that. And so here, to do this one, I'll say sine of phi, and that's of course SOHCAHTOA, and so that's opposite over hypotenuse. And so for us, that's going to be cx again over this absolute value of c. And so when I go through to solve for cx, I get c times sine of phi. And so now here's the important part is this is just like the magnitude of this cx here. And so if we could even sort of write the magnitude there, this is just the magnitude of that x component. And so if we look over here at our x and y, this is sort of very obviously pointing in the negative x direction. And so if we were to represent this vector, I would then call it negative magnitude of the vector c times sine of phi. And of course, if I could also go through and do the same thing for the y. So make sure that that makes sense to you. But so the first thing is that's kind of different about this is the angle was in a different location, so I had to use the sine for the x, which doesn't happen every day. And then because this vector is pointing in the negative x and the y, then to represent this correctly, I want negatives for both of those. So that's a subtle point that'll end up being really important to us as we move on. Now here's a nice conceptual one. So here we have 3 forces in an xy plane. We're saying that this side here, like the y-axis is north and the x-axis is east. So 3 equal forces, F1, 2, and 3. And they're set up this way here. They're all pulling in different directions in the plane. And we want to know is the net force in the object will be closest to which direction. So think about this one and go ahead and pause and think about it and we'll talk about it. Okay, so hopefully you got, like I did, that the answer is northeast. And so what happens here is you can kind of get the feeling that, okay, so F1 and F2 are going to be coming together to point sort of in the northeast direction. And so the big question is which one's going to be stronger, the F1 and the F2 together or the F3? And again, as usual, there's lots of ways to think about this. But what I would do is I would think about F3 as being two components in the north and the east direction. So if I draw these vectors out here, so this would be, if you want to talk about it, this would be like the y component of F3, and this would be the x component of F3. And because these are components, right, they're by definition going to be shorter than the actual vector F3. And so the way that we will add vectors is we'll generally break them all down into like their x and y components, and then you can compare and contrast. And so here in the x direction, F2 is going to be much longer than the x component. And so the overall vector there in the x direction will be pointing something like that. And then F1 is going to be longer than that y component, and so there'll be a little point going this way here. And so overall, that'll end up pointing in the northeast direction. And the last thing, so we're going to continue this conversation of adding vectors, and we're actually going to add two vectors. And so this is kind of the end result of our study of vectors. And so we got two vectors, v1 and v2. We give you their magnitude, and then we draw their arrows to give you a sense of their direction. And so I want to know is what's going to be the total sum of these two vectors, and the way we have it is in magnitude and direction form. So go ahead and stop and give this one a go, and then I'll go through it after. Okay, so hopefully you got choice B, and so let's walk through this. And so the key here is kind of combining everything that we've done. And so we want to represent these two vectors, and I'm going to write them over up here in a format where we have them as their x component and their y component. And so I'll start with v2 because that one's kind of easier. And so for v2, the x component is 0 and the y component is 2.50 meters per second. So hopefully one of your vectors will be nice. You don't have to really do too much thinking with it. Now for the other guy, I'm going to write out its x and y components here. And so we're going to use the SOHCAHTOA. And so what happens here is for this one, this is angle 35. This is the adjacent side. It's the side touching the angle. This is the opposite side. And so in this case here, we can write this out as 8 meters per second times cosine 35. And this one here is 8 meters per second times sine 35. Now I'm kind of skipping steps. I'm not writing out the sine thing first, but hopefully that makes sense to you. And so when I went through and did this, 8 meters times sine of 35, I got that side to be 4.58 meters per second. And then 8 times cosine 35, I got that to be 6.55 meters per second. And so these are both, again, we're sort of doing our traditional XY axis. These are both in the positive direction. So the x would be 6.55 meters per second, and then the y would be the 4.58 meters per second. And so then what we do is to get the total, v total, we just add this up. So the two x components are 6.55 plus 0, so it ends up with 6.55, and then 4.58 minus 2.5 gives us 2.08 meters per second. Now this is the answer. This is the answer in x-y coordinates. The only problem is we were asked us to do this and give us the result in the direction and angle format. And so to do that, I would just take that vector. So again, it's 6.55 and then 2.08. So it's going to look something kind of like this here. So 6.55 meters per second. And then over here is 2.08 meters per second. So we want this guy here. And so first of all, we can find the hypotenuse. So 6.55 squared plus 2.08 squared, square root of that gets us the number 6.87 meters per second. That's the total magnitude of our new vector. This guy here is our new vector. And let's just go ahead and decide we want to find this angle in here. And so what we'll do again, as tangent of phi is equal to opposite over adjacent. And so in this case, it's 2.08 meters per second divided by 6.55 meters per second. What's nice is when you put those on top of each other, they cancel out. And so that angle that we're looking for is going to be the inverse tangent of 2.08 over 6.55. And when I went through and did that, I got 17.61 degrees. And so over here, we just sort of rounded it up. So again, this is something, if you feel like you need a little bit more practice, we have a pre-lecture video on this too to kind of go through, and the book goes through this pretty well. But that's the basics of vectors that we're going to be using an awful lot. All right, thanks a lot.